Hello students, my name is Shayan Mitra, faculty member of Department of Electronics and Communication Engineering of Greater Kolkata College of Engineering and Management. Today's topic is memory organization. So let's start. Subject name Embedded System, subject code EC703A. Lecture number 6. Memory devices. We will talk about the memory organization and memory devices. So let's start with it. A simple create debit transaction card may require just 2 KB of memory. On the other hand, smart card for secure transaction cryptographic functions require 32 KB of memory. A memory, a data byte, or a word, or a double word, or a quad word may be accessed from all addressable locations with a similar process, and there would be equal access time for a read or for a write operation. ROM, read-only memory. Read-only memory is a non-volatility is an important asset useful to embed codes and data in a system. ROM embeds software, application, logic circuit in either forms: masked ROM, programmable ROM, and electrically programmable ROM. Or during runtime programming, EEPROM or electrically erasable programmable ROM, flash memory is used. Masked ROM. One-time masking charge is very high. Therefore, system manufacturer will place order and manufacturing foundry will accept the order for a minimum of 100 pieces. ROM is a cost-effective solution to bulk user. EEPROM. Electrically programmable ROM. It is an ultraviolet ray erasable and device programmable. Erasing means restoring one at each beat. It means it's an ultraviolet ray erasable. It can be erasable in ultraviolet ray. This device is programmable, and in case of erasing, it means restoring one at each beat. In case of each beat, we are restoring the space. As we erasing the data, as each data got erased, in each case one beat, at each beat one has been restored. EEPROM. According to the name, you can see that electrically erasable and programmable read-only memory these are. In case of flash memory, form of a EEPROM in which sector of bytes can be erased in a flash. It means in case of electrically erasable and programmable read-only memory, in case of EEPROM, you cannot erase a sector of bytes in a flash. In case of EEPROM, we will make space for one at each beat. But in case of flash memory, form of EEPROM in which sector of bytes can be erased and sector of space can be available in case of flash memory. PROM, once written, is not erasable. Programmable ROM. It means it is this kind of ROMs is programmable for once. Once you write all the program, can't be erasable. Such like OTP, one-time device programmer. One-time device programmer are the example of PROM. Let's go to the next slide. So what we have now is known as random access memory. A system designer considered RAM device of 8. There are 8 forms. So the forms are SRAM, which is static RAM, DRAM, dynamic RAM, NVRAM, it means non-volatile RAM, EDROM is extended data output RAM, SDRAM, synchronous DRAM, RDRAM is rambus DRAM, 7th is parameterized distributed RAM, and 8th is parameterized block RAM. Uses of RAM: stores variables during a program run or stores stack, stores input output buffers. And in case of RAM, the basic is in random access memory. In random access memory, it consists different kind of registers, and the data needs to be fetched by the processor. Is first the data of the RAM has been fetched at very first by the processor. That's the point. That in RAM we used to store data that needs to be all the executable data are being stored in RAM. It has been it will come from it will stored in ROM for permanent basis, and for program run basis, when we need executable programs, if we need a sequence of programmable instructions or data, we stored it in RAM. Those are executable. So let's start with the different kind of RAM. First is SRAM, which is commonly used for designing caches and in embedded systems and microcontrollers. SRAM means it's a static RAM. In case of static RAM, it's a data it's a static data. It means you cannot just by if power goes off, the data of SRAM usually exists. That's why in designing caches we store, there's a small segment of SRAM has been present or exist to restore or to maintain some amount of data continuity in case of power loss. Data RAM, mostly used in high performance computer, high memory density systems. In case of dynamic RAM, the data process, those are stored in DRAM is faster to accessible. That's why in high performance computers, high memory density system, DRAM mostly used. EDORAM. We have already known what is EDORAM is. EDORAM is extended data output RAM. From the name we can describe the basic features of this RAM. It's an extended data output RAM. Extended data output RAM. So what is that? Used for system having buses with clock rates up to 1000 MHz. It means those buses with clock rates up to 100 MHz use this kind of system. So from the name we can understand that extended data output RAM. So it uses in for system having buses with clock rates up to 1000 microhertz. It means if the clock rates is high, we use this kind of RAM for data output input basis. It's a requirement basis RAM. If the system requires that kind of data where we need a very if we need an extended data output, we use EDORAM for high clock rates. Where if we have to increase the data output, we use EDORAM to help the processor to process data faster for high clock rates. SDRAM. It's a synchronized dynamic RAM. Synchronizes read operations and keep next word ready. It means this SDRAM is also a high performance RAM. In case if the processor is fetching one program instruction, it basically automatically sync with that programming instruction with the next or the programming instruction that is going to be processed next is being ready or synchronized in this kind of RAM. That's why it is known as SDRAM. The processor speed is 1 GHz. RDRAM. Access in burst for successive words in a single fetch. Thus performance 1 GHz speed. This is also being used for high speed access, high speed performance. For high speed performance we use this kind of RAM, which is known as RDRAM. It's a RAM bus RAM. It from the RAM bus dynamic RAM is basically is used for burst mode, for 4 successive words in a single fetch. If we have to fetch 4 successive words, it means it means the RDRAM, if we have RDRAM, it means it helps processor to process faster. All these kind of RAMs are basically included or introduced or being used to speed up the processor. If we want to have a high performance, of a processor, we use this different kind of RAMs have been introduced, such as this RDRAM, which is basically help the processor to fetch 4 successive words in a single fetch. Means it increases the performance of the processor. That's why it's also known as the speed is 1 GHz. It's a high performance RAM. In a high performance system, this kind of RAM has been used. Let's go to the next slide. 6th is parameterized distributed RAM. What it means? It means distributes in various system subunits, input output buffer, transceiver subunits, distribution of buffering of memory, and facilitates faster inputs from input output device. What it means? It means distributes in various system subunits. It means this kind of RAM is basically connected or installed, you can use any kind of word, to increase the overall performance of the system design or the embedded system or the embedded system or the embedded machine. In case where we have embedded system, if we have to increase the overall performance of the processor, the peripherals that has been used, or the input output segment where we have LED or LCDs. So to increase the overall performance of the embedded system, this kind of parameterized distributed RAM has been used. That's why it has been said it is distributes in various system subunits, such as input output buffers. If we connect into parameterized distributed RAM in input output buffers and transceiver subunits, what will happen? The speed of input or the speed of output data will increase. And if we have a power loss, in case of if we have a power shortage, we can manage that using the parameterized distributed RAM. Distribution buffering of memory and facilitate faster inputs from input output device. For input output buffer, input output device, to make all those peripherals and different subsection or different structural unit, to speed up different structural unit and peripherals of a embedded system, we use parameterized distributed RAM. 7 is parameterized block RAM, used when specific block of RAM is dedicated to subunit, such as MAC unit. Used when access by the system or input output or internal bus is slow compared to processing speed of subunit. It means it is basically used, it's a self-explanatory statement that it is used when specified block of RAM is dedicated to subunit. In case of parameterized block RAM, there is a section of RAM that has been specific. It's a specific block of RAM that is dedicated to subunit, used when access by the system, input output internal bus is slow compared to the processing speed. If the processing speed, the speed of the processor is very high, but it is not sync with the any of the subunit of the embedded system, we use a specific block of RAM which has been used or dedicated to the subunit to access the data faster. If we connect a specific amount of block of RAM to the subunit, what will happen? The performance of the subunit or the data that we need to fetch or data we need to send or fed to the subunit, the process of that or the communication, the time of communication will increase. The process of the data will increase. That's why you use the parameterized block RAM. Let's go to the next slide. The summary of a memory: masked ROM, EPROM, flash stores, embedded software, ROM image. Masked ROM is for bulk manufacturing. EPROM, electrically erasable programmable ROM, is used for testing and design stages. These are very important. Masked ROM is for bulk manufacturing. EPROM and EPROM is used for testing and design stages. Electrically erasable programmable ROM is used to store the results during program runtime, erase byte by byte and written during system run. So electrically erasable programmable ROM will be written during the system run. When the system is running, it has been written. The whole instruction set or when the system is running, all the data has been written in the EPROM during the system, and it will always erase by byte by byte. Flash is useful when a processed image, voice data or system configuration has to be stored. What does a flash mean? Flash means we have to erase a block of data. If we have to erase a block of data at a flash of a time, we use flash memory. So what kind of system use flash memory? Image, voice, data. Suppose we have an image. So an image is a coagulation of different pixels, a number of pixels. So it will a specific image will the specific details data of that image will be stored in a ROM. So if you have to delete that, if we select the delete button, it will delete that image. And with that image, the amount of data that basically supports the or the whole image that fed the whole image, that will also be deleted. So a bulk amount of data needs to be deleted. So in case of image processing, or in case of image, voice and data system configuration, the flash memory has been used. If we have a voice recording, if we record that, it will take a bulk amount of register to store the details of the voice data. Now you have to delete that. If you delete that, it will delete the bulk of register. Sorry, it will delete the bulk of space. Basically, bulk of data will be deleted in case of flash memory. And RAM is mostly used in SRAM form. In instruction cache, we use the static RAM. For the continuity purpose, that some of amount of data will be restored or some amount of data will be maintained. Let's go to the next slide. Now, memory selection for an embedded system. Once software designer's coding is over and the ROM image file is ready, a hardware designer is faced with the question of what type of memory and what size of each should be used, such as that what we are talking about. That if we have a camera, a digital camera, then we need a flash ROM. Now, if we have a washing machine, if we have a TV, if we have with different embedded systems, suppose we want to have a LCD display system in a metro rail, so we need, in that case we don't need the flash ROM to work in the system design, but we need a different kind of we specifically need a program, a PROM for LCD display. So these are the case studies that we have discussed here. First case study is automatic chocolate vending machine or real-time robotic control system. Data acquisition system, multi-port network transceiver, fast switches, routers, or multi-channel fast encryption and decryption system. Voice processor or video processing on mobile phone. In case of voice processor, video processing on mobile phone, we use flash memory, flash ROM. In case of digital camera or video recorder system, we also use flash ROM. Let's go to the next slide. Now, allocation of memory to program segments and blocks. Allocation of memory to program segments and blocks. Function processes data and stacks at the various data and stacks at the various segments of memory. Program routines and processes can have different segments. Program routines and processes can have a different segment. You need to have a different segments for processes. The process means the fetching and the mathematical operation that is, or the after decoding all the process that has been happened that has happened on the data, that need a different segment of memory allotment. And program routines, those are also need to be stored, need a different segment of memory. A pointer address points to the start of a memory block. Storing a segment and offset value is used to retrieve for a memory address within that segment. A pointer address points to the start of a memory block. Storing a segment. If we have a segment where data has been stored, and the pointer address will always points to the start of the memory block, and an offset value is used to retrieve for a memory address within that segment. If we have to retrieve a memory address within that segment, we use that offset value. A segment-wise memory allocation in 4 segments: code, data, stack, and extra. For example, image string. Segments and paging at the memory. How we segment the memory block, how we page the memory block, that's the function. Segment-wise memory allocation in 4 segments. For code, we need a different memory allocation. For data, we need a different memory allocation. For stack, we need a different segment for memory allocation. And we have extra also. Segments and paging at the memory. A segment can have a partition of fixed size called pages. A single system, a single segment in which data has been stored, a segment can have if we partition the segment, it will be called pages. Figures of different segment types required by software designer. Now, if we take a close look, the segment types are code, data, stack, extra, and strings. A segment of length 1 bit to 4 GB, overlapping among segments permitted. If you take a close look, that this is the page side. Now, this is the whole segment, and if we partition this is called page. That's why it's called fixed size of 4 KB pages. It's a 4 KB. It's just 4 KB storage. This whole block is 4 KB. This page is can store 4 KB data. Okay. So each segment has a starting and ending memory address. It should have. Each segment has a pointer and an offset address. Using offset code, data is written from segment, as we already discussed. Okay, let's go to the next slide. Different data structures / sets at various memory blocks. Okay. Now stacks. This is the stack pointer. It will address the first holding return addresses on nested cases. This is the stack 1 holding data retrievable set 1 contents. Yes, is a 2-byte address that PC acquires. This is a 2-byte address. A memory block with start and end. So this is a memory block. That's why this is a memory block, and these are the pages, segmented area of memory block. Now stacks. It's an allotted memory block from which data is read in last in first out. Return addresses on the nested cells, sets of last in first out retrievable data, saved context of the task as the stacks. Arrays. One-dimensional or multi-dimensional data can be retrieved from any element address. Queues. Sets of basically in case of queue, the queues are basically used in different kind of register, instruction register, instruction cache, all those kind of register that has been used. The memory allocation process of queues has been used. And if you talking about stacks, in case of ROM, we in read-only memory, the secondary memory, all the data has been stored in the form of stack. So it will help to store the data efficiently in a memory. Now queue use the first in first out. If in a register, if a data goes first, it will goes out first. But if we are talking about stack, if you take a long look, that it's a way of having a bookshelf. It means in a book, if we have a book, if you put that book at first, so we will fill the shelf with books. So the first book will be the last book to be out of the column of the shelf. If we put 10 books, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, the 10th book will be first book to be out. If we have to retrieve the first book, we first have to take out the 10th book. That is the basic data structure of stacks. So to get the second, third, fourth, any book, we need to first put out, we have to get the book that has been put in the shelf at the very last. So all these stacks or last in first out or first in first out, all this data structure has been used according to the usefulness of the memory allocation. If there is a position where you don't need that stack data structure, we'll use first in first out. In register we use first in first out, but in case of ROM we don't need that thing. We need a large data set or large data to be stored, so we use an efficient way of storing all those data, and if we need to retrieve the data, we use that memory address allocation process. We will get the data using the memory address of that data. But in case of register, we use the queue format. What the queues are saying, that sets of first in first out retrievable data, 2 pointer, front head and back head. This is in case of one-dimensional array. That's a register. This is a one-dimensional array. In case of register, in case of queues, we have two types of queues. We have circular queues also. It's a print. Example, a printer buffer. Suppose we put 6 books. It means if we suppose we put 10 pages in a printer, we powered the switch, and as the system process, the first 1, 2, 3, 4, 5, 6 pages that we have already stored in the queue the printer will process the data and it will print the 6 pages. Now after printing the 6 pages, the position of the print, the position of the ink or the position of the ink will get back to its first position. It means that if we have to put other 10 data, if we have to print 10 pages, then we also have to put the pages in the same order. That one, first 2, 3, first one will be in the first and the 10th one will be in the last. So after the 10th page after the 10th page got printed out, we again have to put the same way. So it means it will come back to its initial position after completing the whole operation. It has also said the bound, that's why it's called bounded memory block. We only use that amount of memory block has been used. It will not goes away further. It will not a very huge number of memory is not required for circular. It's a bounded memory block. On exceeding limit, reset to start. Pipe, block queue, example and network stack. Common memory block allotted for a queue with source and destination. This is also known as block queue. Let's go to the next slide. Table. 2-dimensional array, 3 pointers, table base, column index and destination index pointer. Hash table. Collection of pairs of key and corresponding value. It's just like address and data. Key and value. Data set allocated with a memory block, lookup table. As we have a lookup table, we can arrange the data and we can according to the lookup table we can find the key and corresponding value in a hash table. List. A data structure with number of memory blocks, one for each element. Number of memory blocks, one for each element. For each element we have a for each element we have each memory block. Each list element, in each list element stores pointer to next element, last element points to null. It's a memory block. For each element we have a different memory block and it will work like a the element stores pointer to a next element, just like it works like a stack. A list is for a non-consecutive located objects at the memory. That's the important factor. The list is for non-consecutive located objects at the memory. It's non-consecutive objects, located objects at the memory. Yes. That's why we use the list. It has a different process of listing the data. It's a different for different purpose we use different memory value. That's the reason. Okay, so this is the end of the today's. Thank you.